Welcome everyone. I'm Yitzhak. I'm the director of the Israel Institute for Advanced Studies, and it's a great pleasure to welcome you all here to Jerusalem and to the Institute. Our institute was founded in 1975, which is the fourth Institute for Advanced Studies in the world, after Princeton, Stanford, the Netherlands Institute, and us. Nowadays there are more than 400 institutes like that. Well, not like that, because we are the best, but similar. And the Institute hosts research groups and individual fellows. I think thus far we have hosted 200, almost 200 research groups and more than 2,000 individual fellows at the Institute. And apart from that, we are hosting each year 6 advanced schools, like the one you are attending, which is, to my mind, our most important activity, because we are bringing together scholars, the best in their field, with PhD students who are going to be the best in their fields. So let me just wish you a pleasant and fruitful school. Enjoy your stay in Jerusalem. We've arranged a ceasefire just for you. So good luck and have a pleasant time. Thank you.
Thank you very much. Okay. Okay. So can we stop this? Is it possible to stop this? Okay, this noise. Okay. So let me begin. So let me start by. Excuse me?
It's not a problem today.
Well, okay. It maybe just bothers me then. It's going to be a problem not just for the next hour, and that's it. Okay, so let me begin by thanking all of you. It's very nice to see many familiar faces, and it's even nicer to see many non-familiar faces here. I thank all of you for coming. I realize, for those of you coming from afar, coming to Israel is never an easy decision, and in the past several months, I'm sure things have not become easier. So I really appreciate you showing up, and I hope we have a very nice week. I want to also thank the staff of the IIAS, and especially Anat, who's been working really hard to put this all together. I mean, everything that I've done very, very little, and me and the other organizers, and Anat has really pulled everything that you see off. So thank you very much, Anat. And I guess it's a good time also to show you Anat. So if you have any problems, I guess you are, right? You are our person, go-to person.
Yes, totally.
Okay.
Anything, welcome to the Institute, and any problem, question, feel free to join.
And one more thing before I begin. So one more thing. I think even though there is a ceasefire, maybe it's a good idea to know where the shelter is. Not to be alarmed. I hope we don't get to use it, but there's a shelter 2 floors down. Right, 2 floors down, at floor -1, there is a bomb shelter. If the rockets start flying, we go carefully down, slowly, don't trip, and we stay there for a few minutes and then we come back up. But hopefully there's no need for that. I wanted to go over the program, just a few things with the program. So one thing I wanted to say is that tonight we have a reception. So tonight we have a reception and a poster session. So all of you who have posters and didn't hang them up yet, please do so. There are these boards where you can hang up your posters, so please do so before that. And all the rest of us, we're all invited to the reception. Please walk around among the posters. And tomorrow, another special thing that we have is on Monday afternoon, we have an open problem session. If you think of open problems you'd like to share, then you'll be welcome to speak then. There's another event that we have is on Tuesday. We have a tour. It says here that the tour is to the Old City, but we decided to change it. It's going to be to Ein Kerem. So any of you who are worried about going to the Old City, you can join the tour and be with a quieter mind now. And if you want to go to the Old City, just take time off. at some point and go to the old city. It's very nice. One more thing about the schedule. You see that we have lunches at various places, at 2 different places according to the day, so don't be confused. So today, for example, we have lunch in the lobby. There will be some light sandwiches. And tomorrow we have the cafeteria, which is, well, walk with me and you'll see where the cafeteria is. It's a slightly heavier lunch. On Tuesday, again, it's going to be a light lunch of just sandwiches here. And Wednesday, again, the cafeteria. And anyway, you'll see it. It says on the program. Okay. That's it. Okay, so that's what I wanted to say about the program. Let me put up my slides. Wait, where's the mouse is gone. Where's the, sorry, I can't find the cursor. I'm helping you. Good. Okay, so since there are many students and postdocs here, and many people that come either from the area of random Schrodinger operators or from the area of random matrices, we thought it would be a good idea to start off this Midrasha with a very elementary talk, just introducing some basic notions and concepts and some fundamental results and models. So that's what this talk is going to be. It's not really a talk about my work. I think I don't mention any of my work here. So this is what this talk is. I should apologize for something that I decided to do in this talk. I'm not going to mention any names, well, except for names that come associated with models. So I realize that some people sitting here are responsible for some of the results that I will quote. I thought also that if I start mentioning the names, there's a short chance that I'm going to offend somebody. So I just decided to offend everybody equally. So I apologize for that. If you see something that you did mentioned and your name is not mentioned, and it doesn't mean that I don't recognize it. It's just, well, anyway, I decided to focus on that. It's like more of a class about the basic fundamental results. So I'm going to start off by discussing a few themes that I sort of think are central in these areas and in the intersection. And also, as far as I can tell from the titles of the talks, will be central to this Midrasha. So the first theme is one way in which randomness arises in this area, and that's through the study of transport in disordered media. Okay. So if you want to study transport in medium with disorder, one of the ways in modeling disorder is through randomness. So you look at the Schrodinger operator, which I'll describe soon, with a random potential. So that's how a random Schrodinger operator arises. And through the study of transport, so if you study a quantum particle, the transport is determined by the unitary evolution determined by the Hamiltonian, which I'll describe in a second, which is intimately tied with the spectral properties of that Hamiltonian. So actually, much of what is studied in this area is actually the spectral properties of a Schrodinger operator with a random potential, and that's connected to random matrices. And which leads me to a different way in which randomness arises. So you can also use randomness not necessarily to model disorder, but also to model generic phenomena. So if you expect something to happen many times in many different places, sometimes you want to, and this somehow is supposed to be independent from the details of a model, you want to say, okay, so let's just take it random and see what happens. So that's, at least in mathematical physics, that's one of the ways in which random matrices arise or arose historically. And indeed, many of the phenomena, asymptotic phenomena that you see in random matrix theory appear in many different places, which leads to the phenomenon of universality. So there are many phenomena, as I said, in many different models that appear in many seemingly unrelated models have the same asymptotic behavior. So another way of saying this is that there is a remarkably small number of classes of behaviors, small compared to the number of different models studied. So there's a remarkably small number of classes of behavior, which are called, and these classes are called universality classes often. So that's another theme somehow in this area. One theme that I particularly like, and this is really somehow at the intersection of random Schrodinger operators, random operators, and random matrices, is this theme of infinite versus asymptotic theory. So usually when you study a Schrodinger operator or a random Schrodinger operator, these operators are often studied in infinitely extended spaces. So in RD or in ZD or in some infinite graph or some infinite manifold. And then you study the spectral properties of these operators. And this is what I like to call somehow infinite spectral theory. So this is spectral theory which is associated to an infinitely extended model. Whereas in random matrices, what you usually study is a very, very large random matrix, and you want to understand what happens as the size of the matrix goes to infinity. And that's an asymptotic spectral phenomenon or asymptotic spectral property that you study. And there is a very nice interplay that you can manage between these two types of behaviors. One way of getting an interplay like this is if you take an infinitely extended Schrodinger operator and you restrict it to a very large but finite volume, and you ask what happens to the eigenvalues there. And very often this is the connection between these two areas. Another connection is that you want to understand the limit as the size of the matrix goes to infinity of something. And then the way to do that is you somehow get an somehow infinite object, which is in some sense the limit. Usually these kinds of limits are called scaling limits or scale limits of such things. So this is for me this is the main line of connection between these two seemingly different areas. But there's also various others. So for example, there's many observed phenomena that I will discuss in a few minutes that appear both here and here. And there are also common tools, obviously. So there's some tools that you will see in talks about Schrodinger operators that will probably make an appearance also in talks about random matrices and so on. Okay, so let me now get really into the basic of the basic definitions. So what is? I'm going to start with somehow an introduction about Schrodinger operators. So what is a Schrodinger operator? So actually, okay, I'm not sure, but I guess to me a Schrodinger operator is an operator which is a sum of a Laplacian on some space, usually an RD or ZD. So RD would be just a continuous Laplacian, ZD would be some version of a discrete Laplacian. There are various versions. Plus a potential. A potential is essentially a function, so it's a diagonal operator. It's a function that multiplies the vector that you're acting on. It's a self-adjoint operator, so usually when you take the continuous Laplacian, so it's a continuous Schrodinger operator, it's usually an unbounded operator, so you need to define an appropriate domain for this operator, but still you make sure that it's a self-adjoint operator, essentially. And so its spectrum is a subset of the real numbers. And I want to define what's called the spectral measure. So for any vector in your Hilbert space, and the Hilbert space, so in the discrete case, this will be the square summable sequences on ZD. In the continuous case, it will be just square summable functions on RD. You can define a spectral measure through this formula. So if you look at the right side of this equality, this defines a functional, and this functional turns out to define a measure. I mean, you can, okay, so there are various ways of getting this measure, but so this defines uniquely a measure such that this is true. So the integral over t, over the measure with respect to t, is this thing, and this is called the spectral measure with respect to psi. Okay, this is how I like to define it. For any z, this was supposed to be z not in R, so any z which is outside of the spectrum. So this is a typo here. This is not for any z in C, because this is not, the resolvent is not defined for every z. The spectral measure decomposes, so any measure decomposes, any measure on the real line decomposes to 3 parts. I mean, you can decompose it to more parts, but essentially to 3 parts. One of the absolutely continuous part, which is just the absolutely continuous with respect to Lebesgue measure, so it looks like that. There's another part which is the sum of point masses, which I call the pure point part of the measure. And there is a part which has no atoms, but is supported on a set of Lebesgue measure 0. So that part is called the singular continuous part. So this is, for every psi, you can decompose the spectral measure like this. And accordingly, the Hilbert space decomposes a direct sum of Hilbert spaces. So there's an absolutely continuous Hilbert space, a pure point, a singular continuous Hilbert space, which are defined according to this. So this means, so vectors here are vectors which only have this component. And vectors here only have this component, and vectors here only have this component in their spectral measure. And the spectra, you can restrict your operator to each one of these subspaces, and the spectrum decomposes into corresponding parts. So you have the absolutely continuous spectrum, this pure point spectrum, and the singular continuous spectrum of your operator. So the different components, if you look at the dynamics generated by your operator, the different components have very different properties. So the absolutely continuous spectrum is usually associated with good transport. So one way of thinking about good transport is if you look at the, so maybe I try to draw something, whoops. So I'm going to use very little of the board. So suppose this is your space, and you draw a little box. So if your function has only absolutely continuous, has only an absolutely continuous component in its spectral measure, then if psi 0 has only an absolutely continuous component in its spectral measure, then as t goes to infinity, it will the psi of t will have a smaller and smaller part inside any finite box. So this is something that characterizes absolute continuous spectrum. The pure points part is associated with bad transport, so there are various ways of formulating this. One way of saying this is that, this is the simplest way, so this is very somehow, is there a, very simple way of saying something like this is just, so for example, if psi is an eigenfunction, you can see that e to the minus I h t psi is just e to the minus I e t psi, where psi is such that a psi is equal to e psi, which means that psi doesn't really, in some sense, doesn't really move, right? So psi of t and x is equal to psi of 0 at x at every point. So maybe this is something I should say. I didn't say this, but maybe it's a good idea to say that the square of the modulus of this function is supposed to tell you what the probability density of finding a particle described by this function at a certain point. Okay, that's somehow a quantum mechanical axiom. And the singular continuous spectrum has various different types of behavior, and I don't really want to get into this. I like to think about the singular continuous spectrum as an unhappy family according to Tolstoy. So there are various different reasons for being singular continuous, very different ways of being singular continuous. So okay. So that was all the infinite spectral theory of Schrodinger operators. Not the whole thing, but this is just an introduction. And I want to say just something about an asymptotic spectral theory. So as I said, I can restrict my operator to a box. So you take some box of side length L in RD or ZD, and you take the restriction of H to lambda L with some boundary conditions. So restriction means I take, you remember that H was the Laplacian plus a potential. So you just restrict the Laplacian to the box, and you take the restriction of this function to this box. Then you get an operator with a discrete spectrum. In the discrete case, it's even finite. And then you can just take the measure which counts eigenvalues. And you normalize this measure, and in very many cases of interest, and I guess in all cases that we'll hear about this week, that's my bet, this measure converges to some limit. And this limit is called the density of states by many people. Not to be confused with this, not to be confused with the spectral measure. Okay, that's a very different object. And it often has different properties. Okay, so that's just a few elementary notions about the Schrodinger operators. Now, what is a random Schrodinger operator? So in general, a random Schrodinger operator is an operator where the potential is some random field. So in the ZD case, this is just you just pick a random variable in each point of ZD. And I guess the most famous example is what's called the Anderson model, which in the discrete case is the following family of operators. You have you pick some constant, which is usually chosen to be positive. Take the Laplacian, and you take this constant times the potential, and this potential is, as I said, a random field. So V of n in the Anderson model case are just IID random variables. Okay, and lambda is often called the coupling parameter, and somehow it tells you what the strength of the randomness is, or in other words, for physicists, this says what the strength of disorder is. So when lambda is 0, there's no disorder. When lambda is very large, there's a lot of disorder. And there are many, many, many results about the Anderson model. This is not a talk about, sort of a review talk about the Anderson model. I'm just going to say a few things. So under some general assumptions on the distribution of the potential, so distribution, the point distribution of the V of n, so each one of the values of V on sites. So for example, when there's a bounded density, so V has an absolutely continuous distribution, V of n has an absolutely continuous distribution with a bounded density, so the following is known. So for sufficiently large lambda, in any dimension for sufficiently large lambda, the spectrum is pure point, so there's nothing other than eigenfunctions and eigenvalues, basically. And the eigenfunctions are exponentially decaying. So there's a center, and all the eigenfunctions are decay. So for each eigenfunction, there is a center, and it exponentially decays away from the center. And this phenomenon is called Anderson localization. In the one-dimensional case, the same holds for any value of lambda. So as long as there's disorder, there's no transport, essentially. This is what it means. The density of states, which I remind you, this is the limit of the normalized eigenvalue counting measure. It exists and is absolutely continuous with respect to Lebesgue measure. So that's very different from any spectral measure, because all spectral measures will be pure point. And if you take a point where I think you need also continuity of this derivative. So the density of states is absolutely continuous. It has a derivative, therefore. Where the derivative is continuous and positive, you can study the point process, which is take the eigenvalues around E and rescale according to the size of the box to which you restrict it. Okay, so I'm restricting lambda, the operator H. I'm restricting it to a box. I'm looking at the eigenvalues around E, and I blow them up with a factor of lambda L, the size of the box, and I look at the point process that I get, and it turns out that this process, wherever you have localization, this process converges to a Poisson point process with this density. Okay, so in a sense, this means that when you look at your operator restricted to a box, to a large enough box, all these eigenfunctions are somehow independent of each other. The eigenvalues don't see each other. The eigenfunctions are all independent of each other. So that's a classical result now. And there are some things that are conjectured. So it is conjectured that for sufficiently large dimensions, certainly for d greater than or equal to 3, and for sufficiently small coupling constants, so for low disorder, there is some absolutely continuous part of the spectrum. So there is some component of the spectrum which is absolutely continuous. Which is saying actually that what it really says is that if the dimension is sufficiently large, then even if you have a little bit of disorder, there's still going to be transport. which we somehow all know, right? I mean, I heard a talk by somebody that said that he mentioned this as an open problem, and a physicist, he was a mathematician, he mentioned this as an open problem, and a physicist went to the light and turned on the light. He said, come on, this is a proof, because there is disorder, but still transport. So this is the conjecture. This is called, yeah, okay, so this is connected to non-vanishing conductivity in the case of weak disorder. And the associated quantum dynamics should be diffusive in this regime, which means that the extent of travel of a particle in this regime should be over the order of square root of t, with the time. And it's known as the extended states conjecture because it's somehow connected to the fact that one expects the eigenvalues, the eigenfunctions, or generalized eigenfunctions, to not be L2 but actually be extended, to not decay. So this is the name of this conjecture. This is, I guess, the most famous open problem in the theory of random Schrodinger operators, I'm assuming. And since I mentioned the rescale point process, so the rescale point process is conjectured actually to be asymptotic to a point process arising in random matrix theory in the corresponding regime, which should bring us now to random matrix theory. But let me first show you a diagram that I stole from a book, and I should have remained with it. So look there. I'll explain what this is. So this line is supposed to tell you what the spectrum is of an operator. This is lambda, the strength of disorder, the y-axis. As the strength of disorder increases, the spectrum grows. Okay, the spectrum should grow because the norm of the operator obviously grows. But for sufficiently small lambda, there should still be absolutely continuous spectrum. This is where you see this is the bulb. And this absolutely continuous spectrum should grow a bit with lambda. Outside this little shape, everything should be pure point with Poisson statistics. Okay, so this is the picture showing that. Are there any questions about random Schrodinger operators so far? About Schrodinger operators? Okay. Does anybody want to, questions or corrections to what I said? Comments? Okay. Okay, so as I said, that we're being led now to random matrices. So what is a random matrix? So a random matrix is just a probability distribution of the space of n by n matrices. So, for example, HL, so the restriction of H to a box is obviously a random matrix. But that's not what usually people refer to in random matrix theory. Since the basic models of random matrix theory satisfy certain symmetry conditions. So let me give here, the best thing to do is start with some examples. So I guess the most famous example is what's called the Gaussian unitary ensemble. So here's what the Gaussian unitary ensemble is. It's a random n by n Hermitian matrix, M. There are various ways of normalizing it. This is my choice. This satisfy the following. So this matrix should satisfy the following. The entries are independent, so it's a Hermitian matrix, which means that if you know the diagonal, you know what happens. When you know what happens above the diagonal, you should know what happens below the diagonal. But aside from that, the entries are independent. The entries off the diagonal are complex Gaussians with variance 1 over n, which the variance is the sum of the real and imaginary variances. And on the diagonal, you have a, whoops, what happened? And on the diagonal, you have a real Gaussian random variable with variance 1 over n. So this is the Gaussian unitary ensemble. And the point is, this is the same as essentially picking a Hermitian matrix according to the following distribution on the n by n Hermitian matrices. So this is just Lebesgue measure times this density. So you take the trace of your matrix squared and to exponentiate this with a factor of minus n over 2 in front of it. So if you do that and you pick a matrix according to that distribution, you get this ensemble. And the nice thing is that this distribution is invariant under conjugation by unitary matrices. This is why it's called Gaussian unitary ensemble. So the unitary in the name doesn't refer to the type of matrix that you have, but just to the invariance. there are two other classical ensembles. So one of them arises by picking a real symmetric matrix according to the distribution with this density. And this leads to the Gaussian orthogonal ensemble. So this is invariant under conjugation by orthogonal matrices. And if you pick a quaternionic symmetric matrix according to this distribution, that leads to what's called the Gaussian symplectic ensemble, invariant under conjugation by the symplectic group. So these are, I guess, the fundamental classical models of random matrix theory, at least the Hermitian ones. All of these are all of those real symmetric somehow. Okay. With spectrum on R. Okay. The nice thing about these ensembles is that you can compute the marginal distribution of the eigenvalues. So you can essentially integrate out the eigenvectors, and you get the following distribution on eigenvalues. So if you want to know what the probability is of having E1 up to En as eigenvalues, this is what it is, where beta is 1 in the case of Gaussian orthogonal ensemble, 2 in the case of Gaussian unitary ensemble, and 4 in the case of Gaussian symplectic ensemble. And you can write this distribution in the following forms. You can just write this as the exponential of the logarithm of this, which looks like a Hamiltonian of interacting particles. So this is often called the log gas, because the interaction is a log interaction, and you have some kind of external field, which is the x squared. And you can see from this, you can see already from the shape of this, that there's going to be some repulsion between eigenvalues. So you expect there to be some repulsion. And if you look at the eigenvalue counting measure, so again, this is very similar to what happens in the case of random Schrodinger operator. You can take the counting measure and you normalize it. And this, in all these models, converges to what's called the semicircle law, which is sort of obvious. The name is obvious from the shape. And you can also look at the scaling limit. Again, look at again the same process. You fix an energy or a point inside minus 2, 2 in the bulk, inside the open interval minus 2, 2. And you look at the rescaled process. So you look at the eigenvalues around this point, and you rescale it according to the so this density and especially, and you blow it up. And this converges to a point process, which has, in contrast with the Poisson process, has some repulsion in it. So in the GUE case, this is what's called the sign process, which is the determinantal point process with the following kernel. So this is called the sign kernel or sync kernel sometimes. And the wonderful thing about these things is that there is a lot of universality. So it turns out that the sign process appears in many, many different models, many of them not even arising from random matrix theory. So for example, there are examples from number theory, so non-trivial zeros of the Riemann zeta function, combinatorics, and various other models. One more point of interest in random matrix theories is studying extreme eigenvalues. So one can look at the largest eigenvalue of a random matrix. It should lie, of course, close to the right edge of the support of the limiting empirical measure. In our case, for the GUE, GOE, and GSE, the way we normalize it, it should be close to 2. And the fluctuations are not of the order of 1 over n, which they are in the bulk. But I mean, the semicircle law decays at the edge. So the fluctuations are of smaller order. And so the distribution, so these are of order n to the minus 2/3. And now if you want to look at study the scaling limit, you need to multiply this by this factor, and then it converges to a distribution called the Tracy-Widom distribution, which again turns out to be universal. So it turns out to appear in many, many seemingly unrelated models, such as random growth models, random permutations, random tilings. There are many, many different models where this arises. So this is just a somehow crash course, I guess, on random matrices and crash course on random Anderson model. And I want to say a few things about connections. So one connection that I know very, very little about is through random band models. So what do I mean by a random band model? So if you think about a one-dimensional Schrodinger operator, say on the half line, then it looks like this. There's the potential V1, V2, so on, and this would be this basically the Laplacian. Right. So there's only randomness on the diagonal, whereas the random matrix has randomness all over, in a sense. So a random band model is supposed to somehow how do you say this? Interpolate, thank you very much. Interpolate between these two models. So you take a model which has randomness on some band. Okay, on some band of size usually denoted W. So these are random band models, and you want to study these models. And so this is the size of the band, and you assume you have a matrix whose entries are negligible for outside this band. And in this case, it is conjectured that for W greater than square root of n, eigenvectors should be delocalized and statistics should obey GOE asymptotics. So this is where, when the band is sufficiently large somehow, n is the size of the matrix. And for W smaller than that, you should see localization. And there are results about this. I'm not mentioning any of the results, mostly because of my ignorance. I don't want to get into this. There are many works on this, and very interesting, but I really don't want to. So I'm just mentioning this model, and there are people in the audience who know a lot about this model. So if anybody's interested, go to that. So that's one model that I felt like I wanted to mention. Another model that I feel more confident talking about is what's called the Jacobi matrix, which leads to several different connections between random matrices and random Schrodinger operators. So what is a Jacobi matrix? So it's essentially this matrix. I just wrote a version of this matrix on the board where all the A's were 1, but you can take, instead of ones here, so you can sort of take a weighted Laplacian. So a weighted adjacency matrix on the graph N with a potential which is B. So that's a Jacobi matrix. That's, in a sense, the simplest version of a Schrodinger operator, of a discrete Schrodinger operator that you can think of. And one connection arises through random Jacobi matrices, and it turns out that random Jacobi matrices of finite size, you just take an n by n random Jacobi matrix, these matrices provide a natural setting for the extension of the marginal eigenvalue distribution to general beta. So let me remind you, blah, blah, blah. Where was it? Here. Here, that's enough. You see that here you have a distribution for every beta, which is between 1, 2, and 4. And there is a natural question arising whether you can form a random matrix for every beta, for every positive beta at least. And it turns out that random Jacobi matrices are the right setting for this. And again, there are people sitting in the audience who have actually proven this. But I promised I'm not going to mention any names. So they provide a natural setting for the extension of marginal eigenvalue distributions. You can really find models of random Jacobi matrices whose eigenvalue distribution is exactly what I showed you, but for general beta. And you can use them, for example, to obtain asymptotics of eigenvalue distribution through taking scaling limits of these operators. So that's one way, and this is this theme that I mentioned at the beginning of infinite versus asymptotic. This is one way it comes into play. In a sense, these Jacobi matrices are analogs of what's called the Schrodinger operator with a random decaying potential. So you can take your, I'm going to go back here. Bless you. So again, if this is your Schrodinger operator, you can take Vn to be some random variable xn over n to some power alpha. And if alpha is positive, you get a random decaying potential. So there's random decay in this model, and these models are very well studied, and they have a phase transition. And it turns out that these models, these analogs, also have a phase transition. In this case, it occurs at beta equals to 2. So that's somehow a way to see some phase transition in the case of random Schrodinger operators. So that's one connection through Jacobi matrices. There's another connection through Jacobi matrices, which is through the connection of Jacobi matrices with orthogonal polynomials. So a Jacobi matrix is actually, with spectral measure mu, actually encodes the recurrence relation for orthogonal polynomials associated with mu. So maybe I should say. So what do I mean by this? Just to be clear. So if I have a measure on the line, mu, so supported on the real line, let's say with compact support, so that there's no problem. It's not necessary, but just so. Then I can take the sequence 1, x squared, and so on, and I can Gram-Schmidt it to get a sequence of orthonormal polynomials. And these orthonormal polynomials satisfy a recurrence equation. And this recurrence equation is encoded by a Jacobi matrix. I can write this concisely like this. So if you write P0, P1 at the point x, this is just equal to x times this. So in a sense, the sequence of orthogonal polynomials at the point x is sort of a generalized eigenfunction of a Jacobi matrix. And orthogonal polynomials play a very special role in the analysis of random matrix models, especially in the case beta equals to 2. So for example, is the expected characteristic polynomial if you have a random matrix, so for example, if you have a random GUE matrix, you look at the expected. You look at the characteristic polynomial, you take its expectation, it turns out to be a Hermite polynomial. So if you know the recurrence coefficient of orthogonal polynomials, in many models you can actually use that to study asymptotics of certain random matrix models. And this is there's been many studies on that, and the random matrix models which are most which yield themselves most easily to such an analysis are called orthogonal polynomial ensembles for good reason, because they somehow have this intimate connection with orthogonal polynomials. Okay, finally, there are many non-Hermitian random matrix ensembles, so I'm not mentioning the most general, but I would like to say one thing about the unitary case. So, for example, one could take a hard distributed unitary matrix, n by n unitary matrix. This is what's called the circular unitary ensemble. Its eigenvalues will be on this unit circle. And for many of these unitary models, orthogonal polynomials in a unit circle play a similar role to orthogonal polynomials, to the one that orthogonal polynomials on the real line play to the GOE, and other random matrix models on the real line. And these polynomials also satisfy a recurrence relation. I'm not sure it makes any sense for me to write this down now, but if anybody wants me to, I will. And this recurrence relation can also be encoded in a matrix, actually in several different ways. And these matrices are some unitary analogs of Jacobi matrices. So I'm sure we're going to hear in this week some stuff about unitary, some what's called Verblunsky coefficients, CMV matrices. These are the analogs of Jacobi matrices, in a sense. Okay. So I think I'm done. Yes. So that's what I wanted to say as an introduction. I hope it was clear and I hope it was helpful. If you have any questions, we still have time. So if anybody wants to ask anything. Yes?
So when you were talking about the Anderson localization, you said that you belong to the spectrum, and in the localized regime you would see random matrix statistics.
Not the localization regime, in the extended states regime. Right.
What does it mean? Do you mean just
so it's supposed to be GOE. Sorry, for the Anderson model, the conjecture is that it's supposed to be GOE. Yes. It's supposed to, yeah. That's the conjecture. Yeah.
Can you recall the definition of two measures about the Schrodinger operator?
So definition of, you mean the density of states in the spectral measure?
Yeah.
Oh, sure.
I didn't get what's the
No, that's,
difference.
sure. Okay, so let me start in the opposite way now. Okay, so let's start with the density of states. So what is the density of states? So you have a Schrodinger operator. It's on the whole space. Define the whole space. And now I take my Schrodinger operator and I restrict it to a box. This box I call lambda L. Okay? So it has eigenvalues. So E1, L, E2L, and so on. Okay?
And by
These are
the
just
way,
eigenvalues. Sorry?
Yeah, they are real.
Real eigenvalues. Yeah, I take some boundary condition, and this is just in the discrete case. This is just a finite. So I guess lambda L by lambda L matrix. So the size of this domain matrix. Okay. And it's just a finite matrix in the discrete case. So I have just a lambda L. This is the discrete case, yeah, discrete. In the continuum, you'll have an infinite number of eigenvalues, but that doesn't matter. That's not essential. Okay? And now I look at the counting measure. So this is just a measure which assigns to every set in the real line the number of eigenvalues in it, and I divide it by the size of this thing of the box. Okay? Not always, but often, this measure. Okay. Not always, but often, this measure has a limit. So this limit is called the density of states. It counts how many states you have. If you look at the spectrum, in a sense, it somehow measures the density of states. It measures the density of eigenvalues in that interval. Okay, right? You see that this, in a sense, for any lambda L, what this does is tell you how many intervals you have, how many eigenvalues you have in an interval. Okay, so that's called the density of states. Okay, that's the measure, and this is somehow very similar to things you look at in random matrix theory. For a Schrodinger operator, sorry. Now, suppose, forget this finite dimensional picture, or finite picture, rather, and just consider an operator on the whole of space. So you have an operator defined on all of Z2. The corresponding Hilbert space is L2 of ZD, L2 of Z2 in this case. Okay? And for any vector in Z2, I can look, so H minus Z, if Z is outside the spectrum, this is a bounded operator. H minus Z inverse is a bounded operator. Okay? If you want, I can define it somewhat differently. So for any, let's do this in the bounded case so it's easy. So for any function from the spectrum of the operator, say to, C, doesn't matter. Let's say continuous, I can define this object, f of h. This is an operator. Okay? For any function which is continuous on the spectrum, I can define f of h. This is an operator, right? So I can apply f of h to my vector psi, and then take the inner product with psi itself. This gives you a functional on functions. And you can show this as a positive bounded linear form, right? So this means that there is a measure such that this is the same as f of t, d mu of t. So this measure is called the spectral measure of psi. Okay, so that's a different thing. If you want it in a certain sense, what mu psi measures and the spectrum is in a sense the size of the projection, so the norm, the L2 norm of the projection of psi onto the eigenspace corresponding to that part of the spectrum.
But it looks like some
Yeah.
what's called Stieltjes.
Yes, this is the Stieltjes transform of this measure. So I'm defining this measure through the Stieltjes transform. Exactly. So this is right. I mean, you can show that this is a Herglotz function. You can show that this is a Herglotz function, which has asymptotics 1 over z as minus 1 over z as z goes to infinity, and this corresponds to a measure. You know that there is a theorem, right, which says that any Herglotz function has a measure behind it. This is the spectral measure of psi.
But for the measure, it seems like it's the same measure of the. It's
Same
just
measure of what?
the measure of the eigenvalue.
No, because this depends heavily on psi.
Oh.
It depends on psi.
It's not the trace.
Okay, it's not the trace of the operator. It's a. I'm not just looking at all the. I'm just picking one function psi, and I'm looking at this. So this really measures what the function psi somehow. For every e, this measure measures how much of psi is on this eigenspace. Okay.
Physicists call it local density.
Local, yeah. That's why it's confusing. So that's why I made a big deal of saying this is not the same thing, right? More questions or comments, corrections? Yes.
Is the stochastic area operator one example of the random Schrodinger operators?
Which stochastic operator?
Stochastic area operator.
Oh, stochastic area operator. Well, I don't, what does resemble mean?
So you have a Laplacian plus median x and then a y noise.
Okay, yeah.
Brownian motion.
Okay,
Is
yeah.
an example of this general.
Yeah, it's a random Schrodinger operator in a sense. So it not only resembles, it really is a Laplace. Well, I mean, you know, this is not a random Schrodinger operator. Like what I gave is not a mathematical definition. This is just a. More? Okay, then we have a 30-minute break, I guess, right? Do we have a 30-minute break? Yes, we have a 30-minute break, and thank you very much.